So morning everybody. My name is Carsten Merker. I'm one of the Debian developers who are working on the Debian RiscV port. And today I'm going to tell you the story of how the Debian RiscV port came to life, what we have achieved until now, which obstacles we had to tackle to add a completely new architecture to a binary distribution like Debian. I'll show you what we have achieved, what we are planning to achieve, and give you an outlook about what we hope to have within the next 1 and 2 years. I'll start with a short introduction of the RiscV architecture because I know there are people around here who come from the Debian side, not from the RiscV side, and are not familiar with the details of RiscV, so I keep it short. So what's RiscV? RiscV is a CPU instruction set architecture that has been designed at the University of Berkeley, originally as a student project, has grown a bit since then, and everybody is free to implement CPUs based on the RiscV ISA. And the specification that defines this ISA is available under free license, under CC BY. And to make sure that implementations actually conform to the specification, the RiscV Foundation has registered trademarks on the name RiscV, and you're only allowed to call your implementation RiscV if it actually conforms to the spec, to make sure that we don't get incompatible implementations. The RiscV ISA exists in 3 different variants. It's available in 32-bit, 64-bit, and still work in progress 128-bit. So for practical purposes, it's 32-bit and 64-bit right now. It has been designed to be modular, to scale from microcontrollers up to supercomputing, and the ISA designers are trying to have only non-patentable technology in the ISA specification so that it is possible to actually implement a RiscV CPU without having to buy patent licenses. There is no formal legal guarantee for that, but the designers have put quite a bit of effort to make sure there are no patent problems. So we know what RiscV is, what RiscV is not. RiscV is not a specific CPU. It's just an instruction set architecture, the set of commands and the behavior, but not a specific chip. And while the specification is under free license, there's of course the possibility to implement proprietary CPUs based on the ISA. There are already some. And one thing that's somewhat of a problem for open source projects is that the stewardship of RiscV in the hands of the RiscV Foundation is open in the way the semiconductor industry defines the term open, but not exactly in the way open source projects define the term open. All the specifications, once they are released, are available under free licenses, so no problem with that. But taking part in the specification process itself requires a RiscV Foundation membership, which requires signing a non-disclosure agreement, which is why many open source developers like me are not a member of the foundation. Most of the software stuff is actually handled outside the foundation, but the actual ISA specification runs inside the foundation, and getting access to pre-release documents actually requires membership. Everybody can become a member as a personal member, but personal members don't have voting rights, so actual decisions get made by corporate entities in the foundation. So why is it called RiscV? That's rather easy. It's a classical RISC architecture, like there have already been a lot. And it's the 5th major RISC architecture designed at Berkeley, so the name is rather obvious. There have been other RISC architectures, for example, MIPS. If you have a DSL router at home, chances are about 95% that it's MIPS-based. If you're carrying a smartphone, it's about 95% ARM-based. And there are several others. Most of them are closed architectures designed by companies. MIPS is just now slowly changing. There is opening up a bit. Sun Microsystems has actually specified Spark in an IEEE standard, but that standard itself is not freely available. So one has to buy the standard, which again is not nice for open source communities. There has been OpenRISC, an actual open CPU instruction set architecture. So why yet another one? There are already so many to choose from. RiscV has been designed at university. One of the targets of the architecture has been teaching. And closed architectures are not suitable for teaching because you're legally not allowed to just implement an x86 CPU without having a license from Intel and AMD. Spark has the problem that it's only halfway open, and the Spark designers have actually made some choices that, well, people wouldn't do now, today. And OpenRISC is a fully open design, but OpenRISC has a historical problem. Originally, when OpenRISC was designed, one of the GCC porters for OpenRISC didn't allow the copyright assignment of his code contributions to the FSF, and the FSF requires a copyright assignment to get code in GCC upstream. Without this copyright assignment, support for OpenRISC could never go upstream, which is why all efforts to broaden the use of OpenRISC have actually failed. Right now, this has changed. An OpenRISC developer is right now working on re-implementing all the OpenRISC GCC support and getting it upstream. But, well, in the meantime, we have several years of RiscV, so we'll see. RiscV has been designed to avoid some of the decisions that older architectures have had. It's designed to be easily parsable, to be easily implementable, and to be extendable at the same time. We'll get to the extensions in a few minutes. One thing that's important is that RiscV follows a strict upstreaming policy, so all toolchain stuff is handled in upstream. So we don't want 5,000 forks of bin utils, compilers, whatever. We want to have everything standard in upstream. The ISA itself consists of several modules which are labeled with characters, as you can see there. There's the base ISA, which is just the integer operations. There's hardware multiply, atomics, single and double precision floating point, and all those together are called the general purpose set, which is what one would expect for a system to run Linux, BSD, whatever. Then there's the compressed instruction set, which is actually not new instructions, but a shorter encoding for existing instructions. Normal instructions in RiscV are 32 bits long. The compressed instructions provide a selected set of instruction with a shorter 16-bit encoding, which has the advantage of having less cache pressure, having less memory bandwidth requirements, better performance. And if one wants to specify which bits of the ISA CPU supports, you get an ISA specifier like you can see below. IMAFD is RB64G. When the Linux distributions have started porting for RiscV, we had to decide about whether to assume the compressed extension as available or not. That had some discussions at that time. All the binary distributions that are working on RiscV support right now assume that the C extension is there. There is work on a platform specification which defines that all RiscV Unix-style platforms shall have the C extension. The ISA has 3 privilege modes. Machine mode is the highest level. Microcontrollers usually only implement machine mode. If you want to run Linux or BSD, you need all 3 modes. The 32, 64, and 128-bit ISAs are actually independent from each other. That's probably strange to people who are used Intel architecture, where every 64-bit CPU also runs 32-bit code. That's not the case on RiscV. We have a similar effect on ARM64. ARM64 CPUs can optionally support 32-bit code, but they don't have to. And actually, there's quite a bit of ARM64 servers which only run 64-bit code and no 32-bit code. Short side note on Meltdown and Spectre. In discussions about RiscV, often people claim, yeah, RiscV is the solution to Meltdown and Spectre. It's an open architecture. We won't have any problems with that. It's just nonsense. Because Meltdown and Spectre are implementation bugs. They are not a bug in the design of the instruction set architecture, but in specific chip implementations. So while currently we have no RiscV chips which do speculative execution, which is the base for Spectre and Meltdown. So currently there is no RiscV chip that's vulnerable. Nobody can guarantee that that won't happen in the future when we get chips that do speculative execution. So now we have an ISA, but if we want to use an ISA, we would like to have hardware, or at least otherwise run code. There are multiple options. We can do QEMU emulation. QEMU has support for both user space as well as full system emulation. We have CPU designs which can be instantiated in field programmable gate arrays. I'll get to that later on. And we also have real CPU chips. Last year at FOSDEM, we had the presentation of the Sci-Fi Freedom U540, which is the first Linux-capable RiscV chip in the world. There is the LORIS project, which is working on designing a community SOC, but that's still a lot of work, and until we actually have those chips on our desks will probably take 3, 4, 5 more years. Doing chip design is hard, and well, it needs work and needs to be paid. Then there's Shakti. Shakti is a project in India which aims at designing a full family of RiscV chips from small IoT-style embedded stuff up to supercomputer hardware. And the Shakti team has recently actually taped out their first locally produced Linux-capable chip. So what you here see is a picture of actual RiscV hardware. The left one is the prototype that had been presented at last FOSDEM. The right one is one of the early glibc development systems. That is the prototype chip. That is an FPGA board which acts as Southbridge and provides PCI Express. And that's a PCI Express NVMe SSD. So why porting Debian to RiscV? From a philosophical point of view, Debian and RiscV are a perfect match. We have open source hardware, we have open source software, and we would like to combine those two. There have been efforts of porting Debian to OpenRISC, but those have not been successful because of the GCC problematic, because we would have to have shipped different GCC versions on different platforms, which is something that Debian does not do. Debian uses the same versions on all platforms, so that was not an option. The RiscV ISA is probably the first open ISA that has a realistic chance of actually gaining mass market traction. There are a lot of companies supporting RiscV right now, and things in the semiconductor industry are slowly changing. It's become slowly possible to actually have community-led chip production. It's still very much expensive, but things are changing in the industry, and within a few years it might be possible to actually have community-led chip designs mass-produced. Yeah, the first work on porting Debian has started in early 2015, and at that time a lot of stuff was still in movement. Binutils GCC were changing every day. glibc was in its early infancy, the Linux kernel as well. Things have been changing about every 2 days, and code generation actually got incompatible from 1 week to another because of changes in the compiler in the binutils, which meant, if I build stuff today, I probably cannot link it against stuff built in 2 weeks, which is kind of sad if you want to do binary distribution. Then there was somewhat of a culture clash between people from the hardware design world and from the software design world that took, say, half a year to sort all that out. And another problem was at that time we had no QEMU support, so there was only Spike. Spike is a CPU architecture emulator which emulates a basic RISC-V CPU. It only emulates a block device and a dump serial console, but no network. So think you want to bootstrap a distribution, you build a root file system with something, you want to compile something and find, okay, I need another bit of software. Well, normally you just download it, but if you have no network, that's kind of difficult. So shut down emulator, unmount block device, mount block device on host, copy files in, unmount block device, start emulator again, start working. If you have done that 20 times, you want something else. Yeah, due to the ABI breaks and the incompatibilities in the toolchain, all early attempts at actually building packages have not been successful. So both Fedora and Debian developers have chosen instead to work on getting stuff upstream and getting stuff binutils, GCC, glibc, kernel stabilized, so that we have a stable ABI and can be sure that stuff that we build today still works tomorrow. That included some modifications to the linker for Debian-style multi-arc support. That included getting an agreement about using device tree for hardware description, similar to what we use on ARM and on PowerPC, and recently also on MIPS. And, well, things were looking quite well until early 2016, and we had some form of déjà vu, because we wanted to get GCC support upstream, and the people who wrote the GCC support were happy to do a copyright assignment. Unfortunately, some of them had work contracts with the University of California, which gave the UCB the copyright in some of their contributions. And UCP was happy to license the stuff under free license, under GPL, under BSD, no problem. But they were not willing to agree to a copyright assignment. So we were exactly in the same situation that the OpenRISC people had been facing beforehand, and things were looking rather dire. It took nearly a year to get the legal stuff sorted out. So end of 2016, the stuff could actually go upstream, and from then on, binutils and GCC went rather fast. Just a few weeks after the legal stuff had been sorted out, binutils went upstream. 3 months later, GCC was upstream. Then came glibc and kernel. The glibc and the kernel are very much dependent on each other because they use low-level interfaces. And getting that specified out so that the glibc people were happy and that the kernel people were happy took nearly a further year from there on. So effectively, at last FOSDEM, exactly 1 year ago, we were there that we had toolchain, kernel, things were working, things were upstream. We could start with a bootstrap of the distribution. There were some tools that were still missing. GDB Linux support is still missing. We have bare metal support, but not for Linux debugging. As you have heard probably in the talk before, LLVM and Clang support is still work in progress. We hope to sometime this year have a release that will properly work for distribution users. Java has been a problem. We have Java support now, but only interpreter support, not just-in-time compiler support. So Java works, but it's dog slow. Getting JIT support is still quite a bit of work. Rust depends on LLVM. Golang is something that, to my knowledge, nobody is working on.
I worked on Golang earlier, so
Okay, somebody is working on Golang.
Where's Golang?
And then there are, of course, other languages and other compilers. V8 is the JavaScript engine for Node.js, which is also not working yet. So now we have compilers, we have binutils, we can build code, we can build packages. But we're starting from scratch. We have nothing for the RiscV architecture. So how do I get a distribution from thin air where I have nothing? Well, I need a cross-compiler. So I run a compiler on a PC, but generate code for RiscV. And make use of the Debian multi-architecture support, which allows us to have code for multiple architectures within one root file system. So I can gradually generate packages for a new architecture. That, of course, requires getting RiscV support into the toolchain packages that we had in Debian. But as the support had just been released a few weeks ago, the binutils GCC packages in Debian, of course, did not yet have RiscV support. So the first step was actually packaging new versions of all that and getting them into experimental. Then, how does one start in bootstrapping a new architecture? I need a base set of packages. So which packages and how many are that? Well, Debian has package priorities, and the packages with the priority required are the base package set. And well, priority required, okay, that's easy. Just a handful of packages. That's 55 packages. That's no problem. Well, actually, it is. Because those packages have dependencies. They want libraries. And those libraries have dependencies themselves. And to be able to build those libraries, I need a lot of other stuff. So I need dependencies of dependencies of dependencies of dependencies of dependencies to build stuff, which ends up in several hundred packages. I've stopped counting at nearly 400. One of those problems is that, for example, if you have source code that uses Meson to build, Meson uses Python. And building Python is a problem insofar as Python has lots of dependencies because Python has modules for a ton of stuff. And to build Python, the Python package, you have to have all that stuff. So that gets a rather large dependency chain. Dependency issues are twofold. One are deep dependency chains, as I've just shown an example. To build one of the command line base packages, we had to cross-build some 80 or 90 other packages just to get the build environment set up to be able to compile a single simple package. Another problem are circular dependency chains, which is where the cat chases its tail. Packages in the base system are, for example, ordered. Audit requires OpenLDAP for building. OpenLDAP, in turn, requires Cyrus SASL for building. Cyrus SASL requires PAM for building. And PAM requires audit for building. So the cat has just found its tail. How to resolve that? We have to build packages with smaller feature sets to just remove certain features from the packages to break the cycle. And doing that by hand is rather tedious, so Debian has a mechanism for that that is called build profiles. So you can build a package with different feature profiles, and during the bootstrap process we actually have added several build profiles to a number of packages to be able to break those dependency cycles. What you see here is a dependency graph of Firefox, just to give you an impression. That on top there is the Firefox source. The boxes that are led to by the brownish lines are direct build dependencies of Firefox. Each of those build dependencies has runtime dependencies, which are all those bluish lines going to different packages. And that's just the first level of dependencies, because all of those bluish packages have build dependencies on their own, which have runtime dependencies. So if you look at that graph, you can probably imagine that building Firefox comes very, very, very late in the bootstrap process. I've said that we've started cross-building because we had no native code. And cross-building is not as easy as doing native builds. Several packages which build fine natively don't cross-build properly. There are differences in cross-build support in different build systems. People often say GNU Auto Tools, old stuff, ugly stuff, M4, just leave me alone. But GNU Auto Tools has one major advantage. Cross-building effectively works out of the box. Effectively, everything built with Auto Tools just cross-builds. That's unfortunately something that we cannot say about many CMake and Meson-based projects. Both CMake and Meson have, in theory, support for cross-building. But many packages that use Meson and CMake don't make use of the infrastructure that those two provide. And in practice, we had to fiddle around with many of the Meson and CMake using packages to actually make them cross-build. Perl is, well, just strange. Perl claims to be cross-buildable. Well, the way Perl cross-building works is that the Perl configure script requires an SSH connection to a system already running the architecture I want to build for, and then run the configure script natively on the architecture, which obviously does not work in a bootstrapping scenario. So the only way to build Perl is actually build all the rest. So I have a native compiler and then build Perl natively. Another common problem is generators. Makefiles sometimes compile code, which they then execute to generate further source code. That works on a native build, so if the compiler is running on a PC and the binary I'm creating is for a PC, no problem with that. But in the cross-build setting, I'm running a compiler on a PC but generating code for RISC-V, and the PC cannot just execute the RISC-V code. So that does not work. Proper build systems should take care of that, and in a cross-build setting, use the proper compiler for the code generators. Another option, if one has QEMU support, is using QEMU userland emulation. That helps, but we didn't have that in the beginning. Another thing is that many upstream packages don't properly separate between host arch and build arch tools. So if I, for example, want to call package config to get the GCC parameters for linking to a library, those are at least somewhat architecture dependent. So I need the package config for the correct architecture. And many makefiles just don't take that into account and always call the package config for the architecture the compiler runs on, which is wrong if I'm cross-compiling. And then there are some cases of packages that are not multi-arch co-installable with themselves. That can happen. I'm using a tool to build a package which has a library dependency. And the code I'm trying to compile for RISC-V also requires the same library in a RISC-V version. With most libraries in Debian, it's possible to co-install both at the same time, but there are libraries where that doesn't yet properly work, so we had to work around that. Then there's, of course, general portability stuff. Data type sizes are architecture dependent. How long is an int? Is an int 16 bits, 32 bits, 64 bits? that changes from architecture to architecture. There's endiness, so the way numbers are represented in memory. A very common occurrence is that upstream ships outdated config sub and config guess autoconf files. The FSF recommends that autoconf users should always regenerate config sub and config guess from current upstream so that new architectures automatically get supported. But many upstream authors just put the versions they have used when building the release tarball, which are old, and they don't know about RiscV, so we had to replace those. Another thing that's rather common is atomic support. There is a tiny but important difference how to link in libpthread. There is the -pthread flag to the compiler, and just -lpthread, which just links the library. Problem with that is, on PCs, just linking the pthread library is enough. That works. That's the case for x86 and AMD64. That's not the case for quite a bunch of other architectures. And as most developers probably develop on PC hardware, they just don't look at something like that. So we had to patch quite a number of packages for that. And then there are packages that actually require handcrafting header files for each new architecture. libgg error is one of those examples. Then there's type constraints. We have atomics, but on RiscV, atomics are only supported on native word sizes, not on smaller objects. The PC architecture allows using atomics on arbitrary object sizes. That's not the case on RiscV. We have libatomic, which abstracts that away, so if people use libatomic, that's not a problem. But again, many upstream projects just assume that atomics work on arbitrary sizes because that's just the case on PCs. But that's not true for all other architectures. And then there is, of course, stone-edged stuff like looking in the X11 sources, which doesn't make decisions based on properties like if an int is 32-bit, then do something. If you look into the X11 sources, there's really, if architecture is foo, then list of code. If architecture is bar, then list of code. If architecture is buzz, list of code. And so we had to write just new code for that. We tried to get it upstream, but that didn't work because the X11 developers don't want to add code for new architectures because they say X11 is in maintenance mode and we don't want new architectures upstream. And then, of course, there's the problem of compiler support. We lack Rust. So building, for example, Firefox and some other stuff currently does not work because we don't have a working Rust compiler yet. Yeah, doing all the package bootstrap, getting the ordering right, patching packages is rather tedious, and of course we would like to have that automated. Fully automating that is way more complicated than one would expect at first sight. A Debian developer has some years ago written his master thesis about bootstrapability issues, which has helped a lot. And there's a tool by Helmut Grohne which is called Rebootstrap, which at least as far as possible automates the early bootstrap. So getting binutils, getting compiler, getting various GNU tools, getting several basic libraries, which we were very happy to have. So now we have packages, but we want to have a proper distribution. So we need to get those packages into Debian infrastructure. Debian has two major types of architecture. So regular architectures, which have regular stable releases, get security support for stable releases. And we have ports architectures, which is somewhat of the, well, of the kindergarten of Debian architectures. New architectures usually start in ports because they're incomplete. There might be stability issues at the beginning. And bugs in ports architectures don't influence regular architectures. So just unstable testing, stable migrations on regular architectures still runs even if a package is broken on one of the ports architectures. Then for ports architectures, we have a bit more freedom. For example, the ports architectures have an additional suite in the Debian archive, which is called unreleased, which is allowed to carry architecture-specific patches, which are not in the main package source. This is only for temporary stuff, so the aim is that having unreleased empty. That's the final aim. But while we're working on that, there is some stuff which we currently can only keep in unreleased. So that's where we are right now. We have a bunch of packages. We aim at becoming a regular Debian architecture sometime in the future, but that requires being able to build about 95% of the archive, and we are not there yet. This is a package build graph. The grayish line here has been the percentage of the RiscV packages that have been built. This graph is several months old. The spike that you see here has actually been created by porting the Haskell compiler. At that point in time, we got Haskell bootstrapped and built a bunch of Haskell packages which gave that rise in available packages. Unfortunately, the number of packages actually has dropped down again in the meantime, because we have some packages which we had been able to build in the past, but which we cannot build anymore. One of the problems is that several upstream sources that have in the past been using C or C++ are moving to Rust. So we could build the old C or C++ based versions, but we can't currently build the new Rust-based versions, so we had to drop out some packages. Another problem is the Qt ecosystem, which in the past has had its own C++ parser, which has now moved to using LLVM, which brings us to the problem that we don't yet have LLVM. We are currently at 84 or 85% of packages, which provides a rather usable system, but of course it's not everything yet. To become a release architecture, an officially supported, stable release architecture, we need to have Debian installer support. That's work in progress, but not yet finished. We need to have enough buildies with redundancy. Buildies are the package builders Debian uses to automatically compile packages for all architectures. And we need to have everything in infrastructure managed by the Debian system administrators, which have requirements. So they want rake-mountable server-grade hardware, remote management capabilities, which is somewhat difficult with small chip prototype development boards. So that's also something we hope to get within the next years, but we haven't yet. And of course, there need to be people to take care of the architecture. Okay, we have those. The Debian installer support is work in progress. It's possible to build a Debian installer for RiscV from Debian installer Git, but it's not really usable yet. We have two issues that are still being worked on. One is that we have problems with elf utils. Somebody is working on those. That's the last big blocker to get the Debian installer released. Another thing is that we currently don't yet have bootloader support. The U-boot port for RiscV is still rather new. Just yesterday, 2 days ago, the first OpenSPI codebase, which we would need for that, has been published. So that's something that I will look into the next weeks. Then there's the topic of 32-bit support. Currently, we only support RV64, 64-bit RiscV, because that's where most of the work has gone in, where we have hardware. 32-bit support is still work in progress because we don't have 32-bit support in glibc yet, and the kernel support for 32-bit is also not complete because that needs to be coordinated with glibc. And we have the problem that you might have heard of the year 2038 problem, that we have a time type overflow in a few years. And we want RiscV to do that the right way, but that requires infrastructure in the kernel and in glibc, which hasn't been there in previous glibc releases, which is just now getting into glibc. And we didn't want to release a 32-bit port that would be binary incompatible in a few years because we would have an ABI break to handle the year 2038 problem. So that takes a bit. Fedora and Red Hat probably won't release 32-bit ports. Debian might do it, we'll see, if interesting hardware becomes available for 32-bit platforms. The way such hardware could become available are small FPGA implementations. Designing CPUs on field programmable gate arrays is a common technique in commercial CPU development. But in the open source field, that hasn't been done very much because for all available FPGA types, one had to have proprietary compiler tool chains FPGA toolchains from the big FPGA vendors. And, well, open source developers don't want to build this stuff based on proprietary tools. In recent years, there has been a lot of effort to reverse engineer the FPGA bitstream configuration format and to implement free toolchains for FPGAs. We actually have one that's fully working. That's Project iStorm, which is packaged in Debian. So you can actually implement a CPU with tools in Debian and run it on an FPGA. There's Project Trellis, which is currently work in progress. There's a talk tomorrow, just upstairs from here, from the Project Trellis project leader, about his support for the ECP5 FPGA series. What's interesting with the ECP5 is that it's about 10 times the size than the small ICE40 that we have supported right now. Problem with the size is I can implement a CPU on a lattice ICE40, but that's more microcontroller class. Something Linux capable with memory management unit in that size is very, very difficult. David Shaw has actually implemented an open RISC CPU on an ECP5 and is planning also to do a RISC-V implementation on one. Then there's Project X-Ray for even bigger FPGAs from Xilinx. That's in rather early stage. Things are moving forward, but I wouldn't hold my breath while waiting. That will probably take 1 or 2 more years until we have something that finally works there. Well, FPGAs are nice. I can actually in place update my CPU. If I have a better version of my CPU, okay, compile it, place it in the FPGA, new FPU, new CPU. But FPGAs have disadvantages. The clock rates that I can achieve are rather low. So if you get 200 megahertz, that's already rather fast. More realistic on cheap FPGAs is something about 50 megahertz, which by today's standards is just slow. Getting fast chips is rather expensive, and compared with actual mass-manufactured ASICs, they use a lot of current. Another problem is getting memory. Modern memory interfaces are very, very complex, and attaching modern double data rate memory to an FPGA is difficult. That requires a specific file layer, that requires an appropriate memory controller. That's not easy. So we have currently only the choice: either use memory that's easier to address, but it's slower and it's more expensive, or if somebody manages to reverse engineer the common DDR PHY layers in the bigger FPGAs, we might be using standard DDR memory, but that will take time. Well, we have FPGAs, but there are also projects for ASICs. I have already mentioned the low-risk project, which is working on an RV64 community SoC. The current development version of the low-risk SoC runs on an FPGA, and it actually runs Debian. The software development for that chip is actually using Debian. Then, of course, if I want to mass produce a chip, there's not only digital logic in it. The CPU itself is digital logic, but I need voltage regulators, I need analog digital converters, I need a random number generator, I need brownout detection to make sure that the voltage doesn't drop too much. So there's a lot of analog technology which you also need to produce such a chip. And there's a spin-off in Colombia, spin-off of the Universidad Industrial de Santander in Colombia, which is working on providing open source licensed analog components for such CPU. There's also an interesting project. Several people will say that's just insane, but nonetheless I find it interesting. The Libre Silicon Alliance is a group of people from the chip design world which are trying to define a standard silicon chip manufacturing process. Currently you have one problem. You want to produce a chip. You go to one chip fab and say, okay, here's my design, build that for me. You have to use a set of standard cell libraries from your fab. You're not allowed to disclose how those look like. So if you want to build your chip in another fab, you can't just take your design to another fab. You have to redesign your chip with their standard cell library. There is no portability between fabs. And the Libre Silicon Alliance is working on defining a standardized process that is actually transferable from one fab to another. They've started very, very small. They currently have done their first prototype chips, which are based on 1 micrometer node size. That's technology from the early 80s. So nothing you could build a modern CPU in, but that's a long-term project. They're estimating a time frame of perhaps 10 or 15 years. So nothing for tomorrow, but nonetheless interesting. And then there's Chips for Makers, which is a project to improve the software side for ASIC design, which also has a talk tomorrow upstairs. They are aiming to produce a community-funded small CPU. This is 16-bit, 32-bit, 68K, Z80 type stuff. And have actually managed to get the design done, but in the first round, the funding for the actual mass production of the chip didn't work out. They're trying to do another run, and we'll see how far they get. So that's my talk so far. Questions?
So you said at least twice that in some cases Rust is a problem, and Rust has a backend LLVM, and because Debian doesn't have LLVM, then you cannot have Rust, you cannot have Firefox, and so on, and you cannot have any other project which uses Rust code. What is Debian doing to handle the Rust-specific patches of LLVM? Because even if you have LLVM,
it still needs to be ported, yes.
It needs to have the Rust-specific patches to LLVM, because the Rust community also has a set of patches which they didn't get upstream to LLVM. So even if you were in a situation where you had LLVM, you don't have necessarily Rust on Debian.
Okay, I try to repeat that because the people on the stream probably haven't heard the comment. So to get Rust, one does not only need to have LLVM working, but there are also Rust-specific patches to LLVM which also need to be ported, which would also need to be done.
To be upstreamed.
Yeah, or to be upstreamed.
And the question is, how is Debian handling those Rust-specific patches for LLVM?
The question was, how is Debian handling those patches? Currently not at all.
Okay.
We haven't actually looked into that yet.
Okay.
Further questions?
Recently, the AR64, how much of the porting to ARM64, the same process has obviously had to have gone through, how much of that helped in this process?
I'm sorry, I didn't understand that acoustically.
Previously, not too long ago, AR64 was ported and brought into Debian. How much of that process of the bootstrapping of that have you been able to reuse for RiscV?
Okay. The question was, Debian has rather recently bootstrapped ARM64, and how much of the bootstrapping procedure have we been able to reuse for the Debian RiscV bootstrap? Actually, quite a bit during the ARM64 bootstrap. Several packages have gained build profiles to make dependency cycle resolution easier, and that has actually helped a lot. The RiscV specific stuff, of course, can't take anything from ARM64, but the infrastructure has gotten a lot better. And there are people like Helmut Grohne, who has written the rebootstrap tool that I had mentioned, are working permanently on making bootstrapability better by fixing cross-architecture bugs, by adding more build profiles. So that definitely has helped.
How was the UC Berkeley copyright issue resolved?
I actually don't know. That has been handled by lawyers behind closed doors, and I have no information about that.
UC Berkeley lawyers or other lawyers with Debian?
Not within Debian. Debian, okay, I just repeat that. How was the legal problem with the copyright assignment of the GCC code to the FSF been resolved? I really cannot tell that because that was something that had been handled between the RiscV Foundation and the University of Berkeley, and they haven't told the public in which specific way an agreement was reached, so I can't tell anything about that.
I totally have sympathy with the work you've been doing, and I see you're doing a good job. It seems that the core package set size is growing. When we were doing RMHF, I think it was about 200 packages, and now you say it's more like 400. What's the worst pain point? I know you mentioned Maison is now building, dragging in a whole bunch of other things. Is that the only big one, or the others?
I'll just repeat for the stream listeners. The question was that the base package set appears to be growing compared to past ports. When 32-bit ARM had been ported, the base package set had been something around 200 something packages. Now we have reached nearly 400. And which problems have been the major pain point in porting? The first major pain point has been Perl, the lack of cross-bootstrapability of Perl, because all of the packaging infrastructure in Debian is based on Perl. So you need Perl for almost everything. So getting Perl ready has been a real problem. The second one, in my view, has been Maison, but perhaps where's Manuel? Perhaps you can comment on that? Can you talk a bit louder? I just don't hear you.
Yeah, sorry. It's the other so one problem was the glibc, which was in experimental. That was why we initially had problems with the bootstrap. And then the one that I remember most first was a problem. Was one of the biggest problems, but the other one was still many packages in the bootstrap, for example, for utils, don't cross-build properly because they need to help to man, for example, to generate the man pages, and this has to run natively. So there are many small changes that packages need still to get the base set, and I think that those were things could help with that. Yeah, and in the media there were patches for utils, for example, but they were not accepted sometimes by the maintainer, or they were running behind. And yeah, I think that there were the main problems with the initial bootstraps.
Okay, I'll just repeat that for the people listening on the stream. One of the pain points in the early bootstrap had been that glibc for RiscV had only been in experimental because we had to use a newer version than all the other Debian architectures. And that caused some compatibility problems in the early bootstrap. And then one problem has indeed been coutils, because coutils uses help to man to generate man pages. And help to man does not work in a cross setting. That took quite a bit of workarounds. That should be resolved in a newer coutils version than we had at that time. But when we did the bootstrap, that was indeed a problem.
There is another important bit with both for UML and glibc. The kernel was not complete. So, for example, there were bugs that they were not resetting sometimes the registers. When got in, so many tests failed, and so on. That was the other one.
That's of course another problem when one builds an architecture in emulation in QEMU, and one has to handle a bug. The problem is the bug in the code I'm trying to debug, or is the bug in the emulation I'm using to run the code? We had some cases where the code actually was fine and the bug was in the emulator, which of course has needed time and a lot of debugging. So having real hardware is of course better, but when you start such a port, often you only have emulators. I suppose the ARM64 port had the same problem. You started with the original ARM architecture emulator. So that's something that's nearly unavoidable if you do an early bootstrap. That is easier if you wait with bootstrapping until the architecture has already broad use, but of of course, you want to distribute software early in the release of new architecture to make the architecture actually usable. Further questions?
So you've been talking about issues with cross-compilation support on different build systems. So now that you have the bootstrap system, do you plan on always just using a native tool chain, or do you try to keep the cross-compilation patches, maybe upstream them to a more reliable cross-compilation system?
We have tried to get the cross-compilation patches upstream. In some cases that has worked and they were accepted. In some cases they weren't, because some people consider cross-build support a maintenance burden, because you have to think of things of which you don't have to think when building natively. And well, some upstream authors don't see bootstrapping a new architecture as a relevant problem for their software. That's unfortunately, but that's reality.
And you also said that the X11 developers didn't accept your patches, right? So do you have then any chance of getting into the regular Debian releases for the RISC-V port?
Yes, we carry the patches in the Debian packages. Okay. But we would have preferred to have them upstream, but they weren't accepted. Just because the upstream developers consider X11 to be in maintenance mode. They don't want feature additions, even if it's just a new architecture. Any more questions?
What kind of recommendations do you have for maintainers who want to achieve cross-platform compatibility, or are you even aware of a Debian RISC-V CI system support of any kind?
We have a CI system running rebootstrap, Helmut Grone's base bootstrap tool, which works with cross-building, and we have Jenkins jobs doing that. So if you have packages that are part of the base systems, it's helpful to look at the Jenkins results and see if your stuff fails. Debian has portal boxes for multiple architectures on which you as a package maintainer can log in on each architecture that Debian supports and try to build your stuff. And of course you can cross-boot. We have cross-compilers in Debian. We ship cross-compilers for all architectures that we support in Debian. So the Debian packaging tools actually support cross-building packages. So you can just say sbuild -- host arch is RISC-V 64, and it runs a cross-compiler and tries to cross-build your package. So if you're a package maintainer, it's rather easy to check whether your stuff is cross-buildable. That's more of a problem. Upstream is more of a problem. We had some discussions yesterday evening about ways to provide RISC-V machine instances to upstream developers to enable them to test build their code and debug issues on native hardware. That's being worked on.
Think long and hard before you spend time bootstrapping a new 32-bit architecture. We've already seen problems in Debian with 32-bit platforms failing to scale. Try and avoid it if you can.
I'll just repeat that for the stream. The comment was that we should try to avoid bootstrapping RISC-V 32-bit, because other 32-bit architectures in Debian are already struggling with keeping up and building large packages. One known problem is building stuff like a debug build of Firefox, which is a problem on 32-bit architectures, in fact. Yes.
I would just like to make a bit of a counterpoint to that. So I'm working on the FPGA tool stuff, and RV64GC is a pretty big ISA, because you basically got to have hardware floating point, and that's not very fun to implement on an FPGA. Even with an ECP5, that's going to be most of your FPGA gone, whereas RV32 is something that can very nicely fit on an FPGA and run quite well. So.
Okay, I'll just repeat that for the listeners on the stream. Counterpoint to that argument, when one is targeting CPU implementations on FPGAs, 64-bit architectures are a problem because they use a lot more FPGA resources than 32-bit architectures, way more than double of 32-bit architectures. And getting a 32-bit RISC-V CPU Linux-capable on an FPGA is quite doable, even on smaller, not tiny, but smaller scale FPGAs. But 64-bit CPUs is a problem in resource usage. Any more questions? Okay, thanks.